Welcome to this video demo of diagonal analysis, based on Griffing's method for fixed model, implemented under Python. Reference for this program is the 1956 publication of Bruce Griffing on diagonal analysis that is readily available online. Please refer to the web link given here. This script is closely modeled after Griffing's 1956 paper, which was performed on a 9-parent diagonal set. As in Griffing's paper, this script analyzes only data from a fixed 9-parent diagonal set. At this time, this version can only process the data variables fed to it one at a time. The number of replications is flexible. A future version of this script will try to extend this setup, possibly try to add a few more parent lines and would be able to process data variables in bulk mode. Griffing's method 4 tests only the direct crosses, no reciprocals, and no parents. It is, therefore, easy to conduct. Due to its simplicity and modest resource needs, Method 4 has become popular, and is the diagonal design of choice of many researchers. This Python script is also very simple to use. One only needs to organize the raw data according to a specific format. Here is an example of how the raw data from a 4-parent diagonal should be arranged. We assume here, for discussion purposes, that all 6 possible diagonal hybrids were field tested in a randomized complete block design, with 2 replications. This is how the raw data should be organized. First, all the crosses of P1 with all other parents, in consecutive order, go to the top rows of the data file. Then, all crosses of P2 with all other parents follow. Continue this systematic process until the data of the last cross, P3x P4, has been added to the file. Once done, your data is ready to be accepted by the script. To move on, I will now paste the file path of the sample data for this demo. This sample data is only a hypothetical set created just to test the script. So, here we go. Note how fast the script processed and printed out the results. Let's scroll up to view the first output. The script initially outputs a printout of the raw data file. Please be advised. It is important to check the original data to ensure that there are no negative or aberrant values, as there will, invariably, lead to erroneous results. This script calculates 2 ANOVA tables. The first is the general analysis of variance, which is like a standard ANOVA table for a variety trial. Only this time, the entries are the diagonal crosses, not varieties. In this general ANOVA, it is important to check the significance of the entries, the key source of variation. If the f-value for entries is insignificant, the partitioning of its variance into genetic effects, as carried out below, is not valid. Remember this important principle. For now, it is left to the user of the script to uphold this principle. In this demo data, the f-value of entries is palpably significant, so we could go ahead and examine the partitioning of its variance. Take a look now at the second ANOVA table below. This is the ANOVA of combining ability, the product of partitioning the variation among entries, or diallel hybrids. As may be perused, the GCA and the SCA variances are clearly significant, thus further validating the partitioning. Next, the script calculates the relative importance of the additive compared to non-additive variance. In this dummy file, the non-additive variance is much more important than the additive variance, as evident from a low ratio of 0.135. In general, the above-mentioned ratio may offer a rough guideline on the choice of breeding strategy that could be applied to the parent in the diallel set. Let us now look at the next important output: the GCA effects of parent lines. The magnitude of the GCA effects, their signs, and the extent of their variances are important to examine. Consider the following points when interpreting the GCA results. A parent with a significant GCA effect in the right direction, positive or negative, with low variance, tends to transmit its good trait more uniformly to its offsprings. Parents like this are usually referred to as good general combiners. Lines that are good general combiners can be useful components of synthetic varieties, as well as other broad-based populations that breeding programs may develop. On the other hand, there are parent stocks that are not necessarily good general combiners, but tend to show significant SCA effects. If the parent lines in the diallel set are advanced lines, the array of SCA effects could be examined. For the exceptional diallel combinations, selected crosses could then be further evaluated for possible commercial release. Incidentally, a quick test could be done to see if the calculations of genetic effects are correct. In principle, the sum of the GCA effects of parent lines should be equal to 0, without rounding errors. Likewise, the sum of the SCA effects of each parent should also be 0. Do this simple test after analyzing your data. The final output below shows the different variances and standard errors that are used to test the significance of genetic effects and in making other comparisons as may be desired. This completes this video demo presentation. But before I finally close it, let me share an important announcement. A downloadable, Unix executable version of this program has been made available here. Please refer to the download link in the file description. You are greatly welcome to use this Python program. If you use it to generate data for use in your publications, the normal courtesy among professionals expects you to cite your source accordingly. The developer of this Python script has provided the proper citation form in the file description of this video. Thank you for watching.